All right, so welcome to the video on one mean t-test, so the hypothesis testing. So in the last video, we talked about how to do a hypothesis test for using a one mean z-test. Now, in this video here, we're going to present a step-by-step method for performing a one mean t-test. All right, so before we even get started, for a one mean t-test to be valid, the following assumptions must be met. All right, so again, the idea is we're trying to do a hypothesis test, meaning we're going to use some statistic that we get from a sample to make inferences about a parameter of a population. So the first assumption we're going to need is we're going to need a simple random sample. So the second assumption we're going to need is that the population be normally distributed. All right, so if the population is normally distributed, then the sampling distribution of the sample mean is also going to be normally distributed. Or if we don't know the population is normally distributed, then we would need a large sample. All right, so a large sample. Large sample meaning our sample size be bigger than 30, and the idea is that if we have a large enough sample size, we know the sampling distribution of sampling mean is approximately normal. All right, so that's why the central limit theorem. In the off case that our sample is moderate size, 15 to 30, we need to check the normality of the data in question by using a normal probability plot. So in StatCrunch, we would sketch the QQ plot. And finally, if we want to use a t-test, we do not know the population standard deviation, because if the population standard deviation is known, we would have a z-test. So question that I just answered right now, what assumption is different between this test and a one mean z-test? Well, in z-test, sigma is known. All right, so that's the difference between these two settings here. While in t-test, sigma is unknown. All right, so equipped with that arsenal there, we're going to go ahead and we're going to run a hypothesis testing on following example 3.1. So a study on children's screen time viewing was conducted by Stanford researchers. At the beginning of the study, parents of 3rd and 4th grade students at 2 public elementary schools in San Jose were asked to report how many hours of TV the child watched in a typical week. The 201 responses had a mean of 15.41 hours with a standard deviation of 14.16 hours. The first question is, do you think the assumptions of t-tests are satisfied? So they're taking a bunch of 3rd and 4th grade students from 2 public elementary schools. So we have a random sample. So the second one is that either our population should be normal or our sample should be large. There's no mention of the population being normal, but what's our sample size? It's 201. Since n is equal to 201, it's bigger than 30. So we have a large enough sample. And now the final question is, do we know the population standard deviation or not? If we look at it, we're given a standard deviation of 14.16 hours, but this is the standard deviation for the 201 responses we had. Not the entire population, but this sample here. So the sigma in this case here is unknown. So we are in the case of sigma unknown, random sample, and our sample is large enough so that the sampling distribution of the sampling mean is going to be approximately normally distributed via the central limit theorem. Now, we are going to use this information to conduct a hypothesis test. So we're going to conduct a test of whether or not the sample data provides evidence at 5% significance level for concluding that the 3rd and 4th grade children watch an average of more than 2 hours of TV per day. So the question is, do they watch more than 2 hours of TV per day? So we're going to set up our null hypotheses and our alternative hypotheses. So one small thing I'd like to point out, we were talking earlier about in a typical week, 15.41 hours. But here we're given 2 hours of TV per day. So if we're watching 2 hours of TV per day, how many hours are we watching in a week? We're watching 14 hours, so that's our null hypothesis. We're going to start from the assumption that the children are watching 14 hours. And our alternative hypothesis is going to be mu is bigger than 14 here, right? So this is because the question said, do the children watch an average of more than 2 hours of TV per day? So since we're interested in determining whether they watch more than 2 hours of TV per day, that's our alternative hypothesis. So let me write that down. Since we are interested in determining whether they watch more than 2 hours of TV per day. All right, so that's why our alternative hypothesis is set up that way. All right, so next up is our significance level. By question, we're looking at 5% significance level, so we're going to look at 0.05. So next up, we're going to compute our test statistic here. And if we go back here, we know what our mu naught is. Our mu naught is 14. We know our sample mean is 15.41. And we know the sample standard deviation is 14.16. Since we know the sample standard deviation and we don't know the population standard deviation, thus we're going to be using a t-test here. And, and the value of t is going to be, it's the same as before, x bar minus mu naught. But instead, since we don't know the population standard deviation, we're going to replace the population standard deviation by the sample standard deviation. So in our case here, our x bar, our sample mean is 15.41 minus our mu naught is 14 divided by the sample standard deviation is 14.16 and sample size is 201. Which is 1.4117. All right, so that's our test statistic here. That's our t-value. If we were to try to find this information on a table, all right, so is that enough information? Is the t-value enough to identify the information from a table? Not quite. We also need the degree of freedom, right? So what is the degree of freedom here? It is going to equal 200, right? So 1 less than the sample size. So we're going to get that the degree of freedom is 200. All right, so now we are trying to determine the p-value here. Remember, the question we are interested in asking is the following. We are looking at a right-tailed hypothesis test, which means in this particular case here, we're trying to find what the area to the right of our test statistic is going to be, which is 1.4117 for degrees of freedom equal 200. Remember, the t-table that we're going to be used is going to be sparse in that it's not going to have all the relevant information. And if you look at this here, so that's the t-table, right? So, and we're going to go and look at the degree of freedom 200. So, in this case, if we look at degree of freedom 200, it tells us 0.1 of the area is going to be the right of 1.290, and 0.05 is going to be to the right, 0.10 is going to be the right of 1.286, and 0.05 to the right of 1.653. So that's the information given to us. So let's take that information and put that on our chart here. All right, so what we know is the following. So let me just use a different color here. So what I know is for degree of freedom 200, if I look at the right of 1.286, the area to the right of that is 0.10. All right, and now if I look to the right of, what was the value here? It was 1.653. So it's 1.653. I know the area to the right of 1.653 is 0.05. All right. So that's the information we have. And remember, limited table means we're only going to be able to approximate our p-value. So based on this here, the area to the right of 1.286 is 0.10. What is the upper bound? What is the largest the area to the right of 1.417 can be? Well, we know the area to the right of 1.4117 has to be less than 0.10, right? Because that number is to the right of 1.286. Similarly, if the area to the right of 1.653 is 0.05, we know that the area to the right of 1.4117 has to be bigger than 0.05. So what that means is for t is equal to 1.4117, p value will be larger than 0.05, but smaller than 0.10. All right, so that's the best we can do if we are using the table that's provided to us. All right, so let's see if this allows us to say anything about the hypothesis test in question here. All right, so again, I know this is slightly confusing, so let me actually go ahead and repeat the explanation here. So we were looking at degree of freedom 200, and what we're trying to do is we're trying to determine what the area to the right of 1.4117 is. We go here, we look at degree of freedom 200, and we realize the area to the right of 1.286 is 0.10, that's how we read it, and the area to the right of 1.653 is 0.05. So I take that information and I put it there. I say the area to the right of 1.286 is 0.10, the area to the right of 1.653 is 0.05. So the question is, what is the area to the right of 1.4117? It has to be less than the area shaded in red, but bigger than the area shaded in purple. So in that case, we know the area has to be between 0.05 and 0.10, which means the p-value corresponding to that test statistic at degree of freedom 200 is going to be between 0.05 and 0.10. So the question now is, based on the information we have, can we reject the null hypotheses by comparing p-value and alpha? So what do we know about the test, the significance level? The significance level was, remember, 0.05. And what is our p-value? Well, our p-value, is it larger than or smaller than our significance level? Exactly. Our p-value is greater than the specified significance level. Which means we don't reject H0. Right. So in the context of this example here, at 5% significance level, the data does not provide enough evidence or sufficient evidence. Does not provide sufficient evidence to conclude that the third and fourth grade, the third and fourth grade students watch an average of more than 2 hours TV per day. Right, so that's what the hypothesis test here is saying. All right, so just like we did earlier for the z-test, we are going to use StatCrunch to see if we can figure out what the p-value is. All right, so again, remember, we were approximating here, but StatCrunch is going to help us give an exact value. So let's go to StatCrunch here. All right, so let me open up StatCrunch again. All right, so what we're going to do is we are going to do a t-stats, one sample. Are we doing it from data or from summary? Do we have all the data, or do we have information? We have summary, right? So all we know is what the sample mean is. What was the sample mean? It's 15.41. The sample standard deviation is 14.16. The sample size is 201. Our null hypothesis was mu is equal to 14, and our alternative hypothesis was mu was greater than 14, and I'm going to ask for a p-value plot. All right, so let's look at this here. So again, we figured out our t-stat earlier, which was 1.4117, but remember, all we could say about the p-value earlier, if we go back to our sheet, is that, p was between 0.05 and 0.10. However, if we use information from StatCrunch here, we can actually say that the p-value is 0.0798. And if I look at the picture I have, we have degree of freedom 200. The t-value, the area to the right of t-value 1.4117 is 0.0798, which is bigger than our significance level 0.05. Since p is bigger than alpha, we know that data does not provide sufficient evidence to reject the null hypothesis. All right, so again, let me go back. So to do this, we're gonna go to statistics, t-stats, we're looking at one sample, and rather than using data, we're using summary. We're gonna input the mean standard deviation sample size, enter the hypothesis test, and if you want a graph, you're gonna select the p-value, and that's gonna give you the p-value for this one here. And using the p-value, given our significance level, we're going to see whether we can reject the null hypothesis or we cannot reject the null hypothesis. All right, so if you go to the handout, there's another example there. And for students present in class, we collected data, right? And the question I was trying to answer was, do I look my age? All right, and what we did was I asked you all to tell me what my age was. I collected that data there, and I have saved it on StatCrunch under file name Guess My Age. All right, so I collected a random, all right, so the random being questionable here, sample from 36 students on what my age was. And at the time of the experiment, I did not tell you what my actual age was. Well, I was 33 years old when the experiment was conducted, and what I'd like you to do is, using that data and using StatCrunch, I would like you to see if at 5% significance level, whether the data provides enough evidence to conclude whether my perceived age is not 33. All right, so at 5% significance level, does the sample data provide enough evidence to conclude that I don't look my age? Right, so what I would like you to do is I'd like you to go ahead and do that, and a separate video answering this exact question will be posted on Moodle. All right, but for this handout, that will be it.